just gonna assume that this is. Correct. So. We do a flood one. sure our mapping is correct. On the right, looks like our movement is correct. So this creates some convex. I'm gonna have to draw this, and then compute the area of this convex object. It's gonna be a very large thing, so I guess what's the easiest way to do this? We do a bunch of it's gonna draw a bunch of rectangles, right? So we do this, and then we add this area, and then do I have these libraries? Oh, I guess it's not a convex hull. How do we do this? Because it's not technically a convex hull, right? So we know how to draw this. Not necessarily convex. For all edges, the dot product. close. This is a very close number. But we're off by a bit. Indentation all got messed up. Is it because we're not all single? Like, what would this give us for? 0, 0, 0, 1, 1, 0, and then y is our yeah, it gives us area 5 because it's not discrete. This should actually be 10. Is there an easy way to hack this in? How do we convert this to something that works? Because this is like assuming it's giving 42. Is there some relevant number here? 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, oh man, like this. I guess you say that the interior is. The interior is 42. Wait, maybe you contribute half of the external. I don't want to sum. I mean, let's just. I mean, it doesn't hurt, right? My indentation is all messed up now. let's add 1 to this result. Let's just try this. Ooh. Okay. Honestly, we're happy with that. We're happy with that. Okay. Nice. Okay. I'm not even mad. We actually got a good solution on this, even though it wasn't that quick. If we look at this, came 75th on part 1. Mostly because our flood fill was a little slow to figure out. I had a bug in it. But let's just go through this problem. Actually, I think it'll make the most sense if we just walk through it. So Lavaduct Lagoon, something about lava, and then we have a set of instructions basically. Our digger starts in some arbitrary position, and then we can ignore the hex codes for part 1. All we care about is these. This is very reminiscent of like very early problems where basically we start somewhere arbitrarily. I said 0.00, and we move 6 to the right, then we move 5 down, 2 to the left, and that kind of draws this out, right? 6 to the right, 5 down, 2 to the left, etc. And we follow this all the way around, and then we get this closed shape. And then it says the trench takes up 38 cubic meters, but this is just the edge. We need to dig out the middle. And so we dig out the middle and we get this filled in, and this is 62 total pound symbols. And the question is, if you follow this plan, how many cubic meters of lava could it hold? So this is pretty straightforward. You just have to parse the input, break it apart, and the way that I decided to do this for part 1 was I made a arbitrary graph, which is like a dictionary, and then I just simulated it. Across every point that we visit, you walk from 0, 0 to 0, 1, 0, 2, 0, 3, because we're going to the right. Just color it in, set the value in the sparse matrix to like a pound symbol. Then when you've drawn the whole thing, I wrote a quick BFS and randomly picked a point in the center of it that I suspected would be in the middle rather than outside of the graph, and then just did a flood fill where I seeded our scene set as the outline itself, which is here. Scene is a set of ground because I called this value ground, and then basically in the BFS I just started coloring. It's a flood fill, right? Well, actually this isn't BFS, it's actually a DFS because it's I'm popping and it's like first in last out. I just colored it in, so then I got out this exact graph. The bug I had is that I wasn't actually coloring it in when I was searching. I was just doing the search. But then once you color that in, the answer is just the count of how many things you have filled in. So pretty straightforward. This number isn't too big on the real input. But the real tricky part is here. Part 2. The elves were right to be concerned the planned lagoon would be much too small. And so it turns out this first part of the instructions isn't relevant at all. It's actually encoded in these colors. The colors were completely irrelevant for part 1. Now they're the only thing that's relevant for part 2. So now we have to decode these. So the way you decode it is the last digit represents your direction. So 0 maps to right, 1 maps to down, 2 maps to left, 3 maps to up. The first 5 digits are a hex number corresponding to the distance that we move in. So it already primes you that this number is massive. Even on this, just on the sample input, there was this much lava. This is in the billions, if not quadrillions or trillions. So clearly we can't simulate this, but it's still a fairly small number of points or edges, right? It's just a really big area, and it's still going to create this closed polygon. And so that's where the trick comes into play. So there's no way that we can simulate this. It's going to be way too big. But what we can do is think of another algorithm. From doing competitive programming and stuff, I figured that there was an algorithm that would solve this for you. So at first I was thinking, oh, this is a convex hull problem, but this is not a convex polygon. It's actually just a simple polygon. If it was convex, there'd be no like internal things that jut in and then jut back out, right? So really the thing that we cared about here is computing the area of a polygon given its points. So when we implemented that, we just took the implementation from our favorite geeks, and by copy pasting this, it used tabs and it completely messed up my editor for the rest of the time, and it's going to prompt me to log in again, which is great. So shoelace formula. I get off this site. Great. So Gauss's area formula. We can do this. It basically, you're using dot products between different points, and then they eventually cancel each other out, and when you sum them all up, it's here. Yeah, 2 times A is the sum of all 2 by 2 determinants formed by the points of the matrix. Great. We get some university level geometry calculus going on here. Or linear algebra, sorry. So this gives us a formula, but the number here is not correct, right? And the reason for that is because shoelace formula here assumes we're actually computing polygons here where each point is infinitesimally small and the edges of our polygon are infinitesimally small. So really, rather than computing a discrete sum here, we're like, imagine a little point in the center of this pound symbol, and it's going across to the center of this one and then across here. So we're cutting off these little strips on the end of the polygon, right? Because if we assume point, maybe this will make more sense here. What if we do this? We'll open up Paint, our favorite tool from another day, and we'll zoom way in. What's actually happening in this problem is if we assume that this is 0, 0 and this is 0, 6, and we draw the polygons, we're computing the area of like this, right? Oh wait, line tool, will that work? We're computing, you know, this area, right? When in actuality, we want to kind of capture this area, like this, which includes the outer edges of the shape, rather than something like this, right? Oh goodness. Anyways, so we're undercounting. So the intuition here, and this was a complete Hail Mary of being off, seeing that the perimeter length, that the area length here, when we use the area formula, and we got 42 here, and the perimeter of this shape was 38 long, we wanted 20 to get close to, if 20 would get us from 42 to 62, right? The perimeter was 38, but the intuition that I had was we want about like half of this strip on the perimeter. So if we have 38, we get 19. 19 almost gets us to 62, right? We're at 61 now if we add 38 to the 42 that the area formula spat out. So then if we just add 1, we actually get there. So maybe it's some weird off by 1 rounding type thing. So to confirm this, when I ran it on the part 2 on the sample input here and did that same math here, perimeter divided by 2, but then we floored it so it's +1, so I guess it's like the ceiling rounded divided by 2 that we want. We got this exact number, 9524081441115. So then it was a matter of just running that algorithm on the real input, and we run it here. It takes a while to compute, but it's just a bunch of dot products, right? This is how many rows is this? It's only 722 rows, right? So it's only computing 722 dot products, and then we get the correct answer out. So yeah, took a while to Google for the correct thing, but I'm pretty satisfied about getting this answer so quickly. Ends up being a quicker day than probably some of the trickier problems. We only have 438 solves so far. I wonder what the speeds were like here. Okay, we could probably get all the competitive programming people up here at the top who have this algorithm handy. But we're 20 minutes to close up the answer. Anyways, feels good to get some points on this. Maybe we can break. I know the goal was 1,000 points. I don't think that's achievable, but maybe 500 points is the goal, or just sneaking to the top 100 by Christmas. But yeah, anyways, that was today's problem. So